Astronomy was silent for centuries. We saw stars and galaxies, just lights, but we were deaf to the real soundtrack of the cosmos, the crashes, the collisions, the things shaping reality. That deafness ended in 2015 with a single chirp, the sound of two black holes merging over 1 billion light-years away. This is the story of gravitational wave astronomy. It's not just adding pages, it's rewriting the whole book on cosmic collisions. You'll see how this new sense reveals a hidden universe, a violent one. Light can never show it. We'll see how collisions forge gold, the gold in jewelry, and why some black holes have masses that defy all expectations. What does it mean for humanity to finally hear the universe speak? That chirp opened a door, but to see what came through, you have to remember the quiet we lived in before. For so long, everything we knew about the universe came from one thing: light, photons traveling across space, hitting our eyes or our telescopes. Astronomy was built on that. And it was beautiful, but it was limited. We could only see what glowed: stars, galaxies, the hot and the bright. It was like trying to understand a dark forest by only watching the fireflies. You could map their little lights, their movements, but you'd know nothing about the trees standing there in the dark, or what else was moving in the shadows. And the universe had so many shadows, things that don't glow, black holes, they eat light, neutron stars, so dense but so faint. When two of those dark things collided, it was invisible. A silent event. We knew they were probably there. We saw stars orbiting nothing, pulled by some invisible, heavy partner. The math said these collisions had to happen. But the moment itself, the crash that actually warps space, that was a mystery. We saw the before. We might see heated debris after, but never the event. Relying on light gave us a strange picture. We thought we knew where the mass was based on what shone. We tried to understand how galaxies grew from the stories light told us. But the whole time there was this hidden symphony, collisions, shaping galaxies, making elements, doing the real work of building things, all unseen. We were missing the most important chapter because we were deaf to it. That chapter isn't written in light, it's written in the shape of space. Albert Einstein. In 1916, he had this theory of relativity, and it changed how we saw gravity. It wasn't a force, it was the bending of space and time, a kind of fabric. A planet sits in that fabric like a heavy ball on a trampoline. Things roll toward it, but his math showed something else, something more. What if that ball wasn't just sitting there? What if it was moving, accelerating, or two heavy balls orbiting each other faster and faster? His equations said that kind of motion, that violence, wouldn't just bend the space around it. It would send out ripples, waves, in the structure of space and time itself, moving at light speed. He called them gravitational waves, and to him, they were almost a curiosity. A beautiful prediction, but he doubted we could ever detect them. They would be too faint. The universe might be trembling, but he thought we would be numb to it forever. But that idea, that seed, was planted. The idea of ripples from a cosmic collision. And for a century, it was a whisper to a few minds. If these waves are real, how do you build an ear delicate enough to hear them? That was the challenge, to move from one man's doubt to a new sense for everyone. The challenge was measuring a tremor so small it didn't make sense. A gravitational wave passing through from some far-off collision. It wouldn't shake the ground. It wouldn't move mountains. What it would do is stretch and squeeze the space between 2 points by a fraction of the width of a single proton. To get that scale, think about the distance from our Sun to the nearest star. Proxima Centauri, that's about 4.2 light-years, an almost unimaginable span. Now imagine you need to measure that entire distance, and you need the accuracy to be the width of a single human hair. That's the precision you'd need to catch a gravitational wave. It felt less like engineering, more like magic. For decades, it was a dream, just a handful of determined scientists. They built early detectors back in the 60s and 70s, massive metal bars designed to ring like bells if a wave passed through, but the universe stayed silent to their instruments. The whispers were there, but they were drowned out by a cacophony of earthly noise. Every truck on a distant highway sent a vibration through the ground. The constant warmth of the room made atoms in the detector jitter. Even the strange rules of quantum mechanics introduced a fuzziness, a fundamental fuzziness at the tiniest scales. The signal they were after was buried under a mountain of interference. It was like trying to hear one specific leaf fall in the middle of a hurricane. That was the barrier, a prediction from Einstein on one side, the cold, hard reality of physics and engineering on the other. To cross it required more than better tools. It demanded a leap of imagination to build an instrument that wasn't just sensitive but quiet, an ear for the universe built in the stillness of the human mind. The leap of imagination took physical form, two huge L-shaped structures, one in the forests of Louisiana, the other in the dry plains of Washington state. Together they were LIGO, the Laser Interferometer Gravitational Wave Observatory. It wasn't a telescope looking up, it was an ear laid flat against the ground, listening. Listening for the vibrations of space itself. Each detector had two arms. Each arm was a tunnel 4 kilometers long. Inside, a near-perfect vacuum. Emptier than the space between planets, down these tunnels they sent beams of pure laser light, bouncing between mirrors suspended with impossible delicacy. The principle was elegant. You split a single laser beam, send a pulse down each long arm. The beams bounce back, they meet and recombine. In perfect stillness, with the arms exactly the same length, the light waves cancel each other out. That's silence, a dark signal, but if a gravitational wave passes through, everything changes. The wave stretches space in one direction, squeezes it in the perpendicular direction. For a fleeting instant, one 4-kilometer arm becomes a tiny fraction longer. The other becomes a tiny fraction shorter. The difference is less than 1/10,000th the width of a proton. But it's enough. The two laser beams, having traveled slightly different distances, they no longer cancel out perfectly when they meet. Their waves go out of sync. They create a flicker of light where there was once darkness. That flicker is the signal, a whisper translated into a visible pattern. That was the genius of the design. It turned an impossible measurement of distance into a detectable measurement of light, and having two identical detectors, separated by 3,000 kilometers, that was the masterstroke. If a truck rumbled near the Louisiana site, it might cause a false signal there, but only a true cosmic tremor traveling at light speed would strike both detectors. With the same distinctive fingerprint, separated by the precise 10 milliseconds it took the ripple to cross the continent. That was the final filter, separating the universe's voice from the Earth's constant rumble. After decades of work and a monumental upgrade to advanced LIGO, the sensitivity finally crossed the threshold. The instrument was now tuned to hear the specific frequencies of the most violent events, the final spirals of black holes, the shattering crashes of neutron stars. The Earth itself was transformed, no longer just a rock floating in space. It was a resonant chamber, a planet-sized antenna pointed at the dark heart of the cosmos. And on a quiet morning in September 2015, after a century of waiting, the antenna twitched. It was September 14th, 2015, early morning. And for a moment, everything was quiet. Then the data stream flickered. A signal came through, first at the detector in Louisiana, then 10 milliseconds later at the one in Washington. It wasn't a long event. It was a brief chirp, a ripple in the data. It lasted just 0.2 of a second. To someone who didn't know, it could have been anything. A glitch, a random vibration, but to the scientists watching, it was a shape, a story written into space itself. They called it GW 150914. That tiny chirp was a death spiral, two colossal objects. The data told a precise story. One black hole about 36 times the mass of our Sun, another 29 times as massive. They'd been orbiting each other for eons, a gravitational dance, slowly losing energy. In their final moments, they whipped around each other, hundreds of times per second. Closer and closer until they smashed together. They merged into a single new black hole, about 62 solar masses. And here's the staggering part. The final black hole weighed less than the two that made it. The difference was roughly 3 solar masses, 3 suns worth of material. Where did it go? It didn't explode as light. It didn't scatter as debris. That immense mass was converted completely into pure energy, the energy of the gravitational wave itself. For that brief 0.2 of a second, the power output of that merger was greater than the combined light of every star in the observable universe. All that power was channeled not into a flash, but into a tremor. A tremor that traveled for over 1 billion years to reach us. With that one signal, everything changed. Einstein's prediction was no longer just elegant math. It was a real thing, a measurable thing happening in the cosmos. It proved that pairs of stellar mass black holes exist. They find each other and they collide. An entire hidden population, a dark sector of the universe, suddenly revealed. We'd been watching a silent movie of the cosmos for all of history, and in that moment we heard our first sound effect. It wasn't a whisper, it was a thunderclap from 1 billion light years away, telling us the silent era was over. That first sound was a collision in total darkness. But the universe had another kind of crash, one you could see. These are neutron stars, the ultra-dense cores of dead stars. You take the mass of our Sun and you crush it down to the size of a city. A teaspoon of that material weighs 1 billion tons. They're the remnants of supernova, spinning cinders, and sometimes they find each other. In August of 2017, the gravitational wave detectors heard a new signal. It wasn't the brief chirp of black holes. This was longer, about 100 seconds, a rising crescendo as 2 neutron stars spiraled in. LIGO in the U.S. heard it, Virgo in Italy heard it. With 3 detectors, they could pinpoint the source in the sky. They sent an alert, point your telescopes there. What happened next changed everything. 2 seconds after the gravitational wave stopped, satellites saw a flash, a powerful burst of gamma rays from that same patch of sky. A short gamma ray burst, then optical telescopes looked. In a galaxy called NGC 4993, about 130 million light years away, they found it. A new point of light, glowing blue, then red, a kilonova. For the first time, we witnessed one event with 2 senses. We felt the ripples in space-time from the merger. And we saw the radioactive fireball it made, multi-messenger astronomy. Hearing the crash and seeing the aftermath, that fireball solved a mystery. Where do the heaviest elements come from? Stars make carbon, iron, but elements heavier than iron, gold, platinum, uranium, they need something more extreme. Theory said they were forged in neutron star collisions. Now we had proof. The light from the Kilonova showed the signatures. These heavy elements were being made right there. In that one event, they made gold and platinum. Several times the mass of our entire planet, the gold in a ring, the platinum in a car, traces in our bodies, likely born in collisions like that, billions of years ago. Seeding galaxies with the stuff for planets and for life. This event, GW 170,817, did more than confirm a theory. It rewrote our story. We are not just stardust. We are, in part, the ashes of the most violent collisions. The silent crashes of black holes showed us a hidden reality, but this luminous crash gave us a new origin. written in gravitational waves and painted in the light of forged gold. That single chirp opened a floodgate. Since that first detection in 2015, the catalogue has grown from 1 to over 90. We're not hearing rare events anymore. We're listening to a constant, low hum of violence, a population speaking, and what these dark objects are telling us is rewriting the textbooks on how stars live and die. The first surprise was the sheer size of some of these black holes. Before gravitational waves, we knew of stellar mass black holes from X-ray binaries. Where a black hole pulls gas from a companion star, those black holes were typically 5 to 20 times the mass of our Sun, but the collisions we're hearing tell a different story. We're routinely finding black holes at 30, 40, even 50 solar masses. Some merging pairs have combined masses over 100 times that of our Sun. Where did these monsters come from? They're too heavy to be the simple remnant of a single star dying alone. The answer seems to lie in the neighborhoods where stars are born. Imagine a dense, ancient star cluster, a celestial metropolis where stars are packed tight. In that crowded environment, massive stars can collide and merge even before they collapse. They form heavier and heavier progenitors, which then collapse into these unexpectedly large black holes. It's a different pathway to oblivion, one that only happens in the busiest parts of the galactic city. Our previous census, based on the quiet X-ray binaries we could see, was missing this entire demographic of heavyweights. Then there are the mixed binaries. The catalogue now includes signals of black holes merging with neutron stars. This is a crucial clue. It tells us about the final fate of certain stellar partnerships. Two massive stars are born together, a binary pair. One explodes first, leaving a neutron star. The other follows, collapsing into a black hole. For them to still be bound together and to eventually spiral in and merge requires a delicate cosmic ballet. The supernova explosions that create these remnants must not have been too violent, or they would have kicked the system apart. Each detection of a black hole and neutron star pair helps refine the story of stellar death. Constraining the kicks and shudders that accompany a star's final moments, every new chirp is more than a spectacular event. It's a single data point in a vast cosmic census. Statisticians are using this growing catalogue to map the universe in a new way. They can start to answer questions. How often do these mergers happen in a galaxy like our own? How does the population of these dark objects change over cosmic time from the early universe to now? What is the distribution of their masses and spins? We're moving from the era of discovery to the era of demography. That fundamental shift is what makes the catalogue so powerful. We're no longer just proving these events exist. We're taking a detailed survey of a hidden society, a society made of ghosts revealed only by the tremors they create when they embrace. The universe we thought we knew, based on the light we could see, was a quiet suburb. The true cosmos, heard through gravitational waves, is a sprawling, dynamic metropolis, teeming with dark remnants, constantly colliding and reshaping the architecture of space itself. Each chirp in the catalogue is a story. It's not a story in words, it's a shape, a ripple with a specific fingerprint. That shape is the gravitational waveform. And it tells you everything. It starts as a faint wobble, a low frequency, just a few cycles per second. That's the opening. Two massive objects in a wide orbit, slowly losing energy. They spiral closer over thousands of orbits. The frequency of the waves rises, the amplitude grows, a faint murmur becomes a rising whine, then a rapid, shrieking crescendo. That final sweep is the chirp, the merger, and then it's over, replaced by a fading ringdown, the new single object settling into its quiet, distorted shape. Every detail of that curve is a clue. The rate the frequency increases tells you the masses. A pair of heavy black holes will chirp up to merger much faster than lighter neutron stars. The way the amplitude grows reveals the spin. Are they tumbling or spinning neatly in alignment? That spin is written into the waveform. Even the orientation of the event leaves an imprint. It tells you if we saw it face on or from the side. But how do you translate the shape into numbers? How do you go from a squiggle on a graph to knowing one black hole was 36 solar masses, spinning at 0.7 of its maximum rate? That's where the forensics begins. Astrophysicists have used supercomputers for decades to simulate these collisions. They solve Einstein's complex equations for millions of scenarios. Different masses, different spins, different angles. Each simulation produces a predicted waveform, a library of possible fingerprints. When a real signal arrives, the scientists don't just look at it. They let the data speak. They take that library of millions of templates and ask which one matches. Algorithms sift through, comparing the detected ripple to every predicted shape. They're not looking for a perfect match, but for the family of waveforms that most likely produced the signal. From that statistical comparison, they extract the parameters. Not as exact numbers, but as ranges with incredible confidence. We can say with near certainty, the lighter object had a mass between 28 and 31 solar masses. That its spin was likely aligned, that it happened roughly 1.3 billion light-years away. The precision is staggering. We're not just hearing a crash in the dark. We're reconstructing the identity card of the participants. From a tremor that stretched our detectors by less than a proton's width, that waveform is a direct imprint of warped spacetime. A message sent by gravity itself, carrying a perfect record of the violence that created it. It tells you not just that something happened, but exactly what it was. A fingerprint from the edge of reality delivered across cosmic time. That fingerprint tells a complete story. It has 3 distinct acts. The first act is the longest. It's called the Inspiral. A cosmic courtship. You have 2 black holes born from separate stars bound together by gravity. They orbit each other for millions of years, billions of years. A slow, stately dance, but with every pass they lose a tiny bit of energy. That energy is carried away as faint gravitational waves, and that loss pulls them closer. Tightens the orbit, increases the speed. It's a death spiral that accelerates over eons. The signal during this phase is a clean sweep, a rising tone. From a low hum to a higher whine, it's the sound of inevitability written into space itself. This part is so clean, so predictable, that we can forecast the final moment. We can know it long before the crash. That crash is the second act, the merger, the climax, the 2 objects whipping around each other hundreds of times per second. They finally touch. Their event horizons, the points of no return, they stretch and merge into a single, wildly distorted shape. For a fleeting instant, there's no longer a pair, but not yet a single stable object. That violent transition releases a storm of energy. The wave signal peaks in a final, sharp burst, a shriek of pure spacetime distortion. It's the loudest part of the entire event. The most energetic. This is where Einstein's equations are pushed to their absolute limit. A regime of gravity so strong nothing else compares. Then comes the third act, the Ringdown. The new single black hole isn't a perfect sphere. It's formed by a violent collision, so it's lumpy, distorted, like a misshapen bell that's just been struck. And just like a bell, it rings. It vibrates in characteristic modes, shedding its distortions as it settles. It settles into a quiet, stable form, a perfect sphere, according to the no-hair theorem. The waves during this phase are dampening oscillations, a fading hum. The frequency and the decay rate of this ringdown, they're like a direct measurement. They tell us the black hole's final mass and spin. It's the cosmic equivalent of listening to a bell's tone to know what it's made of. This 3-act structure, Inspiral, merger, Ringdown, it's more than a dramatic sequence. It's a complete laboratory for testing gravity. Every ripple in that waveform has to match the predictions of general relativity. any deviation, any unexpected wiggle in the signal could point to new physics. Maybe a hint of what lies beyond Einstein's theory, in the mysterious marriage of gravity and quantum mechanics. So far, the waves have sung in perfect harmony with the maestro's score. Each collision confirms that even in the most extreme theater of the universe, the laws we've deduced hold true. The story written in spacetime is one we're finally learning to read. So these waves, in their essence, are a ripple in the fabric of reality, and their speed is a cornerstone of that reality. One of the most profound validations from this new astronomy, it didn't come from a black hole crash. It came from that luminous neutron star merger, GW 170817. When it was detected, the gravitational waves arrived at Earth about 1.7 seconds before the flash of gamma rays. This tiny delay across a journey of 130 million years, it was monumental. It confirmed with stunning precision that gravitational waves travel at the speed of light, exactly as Einstein's theory predicted. The two messengers, one a ripple in space, the other a burst of light. They had raced across the cosmos neck and neck. That 1.7-second difference, it's likely just the time it took for the explosive fireball to punch out from the wreckage. This single observation ruled out entire families of alternative theories of gravity, theories that required gravity to move at a different speed. It was a breathtakingly simple test. A cosmic race with the entire universe as the track and our detectors as the finish line. Beyond just speed, the very shape of these waves serves as a laboratory. As they propagate, do they stretch and squeeze space in the exact manner the equations demand? Do they carry energy away at the precise rate predicted? Every chirp gets this forensic scrutiny. Scientists search for any subtle deviation, any tiny wiggle in the waveform that doesn't fit the template of general relativity. So far, the waves have been impeccably behaved, even in the most extreme gravitational fields imaginable, where space is tied in knots and time behaves strangely. Einstein's century-old theory holds supreme. But the search continues. Each new event, each louder or more unusual event, is a chance to probe the boundaries. Could there be a hint of quantum gravity in the ringdown of a black hole? A faint echo of extra dimensions in the Inspiral. The detectors are now so sensitive they're not just listening for collisions. They're listening for the universe to whisper a correction to its own rules. Every signal is a stress test for the fundamental pillars of physics, conducted in a laboratory we could never build with energies we could never create. And so far, the pillars stand firm, confirmed once more by the silent tremors from the dark. This new sense isn't just confirming old laws, it's making us question an old story. Where black holes come from, for a long time the answer was clear. A massive star, much heavier than our sun, lives a short, violent life. It burns through its fuel in millions of years. Then its core collapses. If it's heavy enough, nothing stops that collapse. It becomes a black hole, and we thought the mass of that black hole was tied directly to the mass of the star's core. Simple, elegant, but the gravitational wave catalogue has thrown a wrench into that. The black holes we're hearing merge are often too heavy. A single dying star, by our best models, shouldn't leave a remnant of 40 or 50 solar masses. The physics of the supernova explosion itself, it blows away too much material. It limits the final weight. So how do we get these heavyweights? Astronomers see two paths now. Very different paths. The first is cosmic cannibalism. In crowded places, imagine a dense globular cluster, a spherical swarm of millions of stars bound in a tight ball. In that stellar city, black holes, being the heaviest things, sink to the center. They start a chaotic gravitational dance. They pair up, they merge. That new, heavier black hole then interacts with others. It can merge again and again. In this hierarchical buildup, a black hole grows through a series of violent marriages. That explains many of the heavy pairs we detect. Their spins often tell this story. If the original stars were born together, evolved together, their spins might be aligned. But if two black holes randomly find each other in a chaotic cluster, their spins are random, tumbling in all directions. The data shows both. Some pairs have aligned spins. Some are completely misaligned. That suggests multiple origin stories are at play. But there's a second possibility, more exotic. What if some of these black holes were never stars at all? This idea points to the universe's first moments. In the heat and density of the Big Bang, tiny fluctuations could have collapsed under their own gravity. Directly into black holes, these would be primordial black holes. They could have formed with a wide range of masses, from microscopic to many times the mass of our Sun. If they exist, they'd be ancient relics, fossils from the first fraction of a second. Some theories even suggest they could make up part of the dark matter. The stuff that holds galaxies together. Gravitational wave astronomy is the first tool that can realistically search for them. How? By listening for their mergers. Primordial black holes, if they formed early, would have their own distinct population. Their masses might cluster in specific ranges. Their mergers might happen in the emptiness between galaxies. Not within dense star clusters, and crucially, we might detect mergers from much farther back in time, from higher redshifts, earlier than the stellar-born black hole population. Every new chirp adds a data point to this cosmic census. By mapping the masses, the spins, the rates, the locations of these events, we gather clues. To perform a cosmic genealogy, we're learning to read the family tree of black holes. Are they the grandchildren of massive stars, built up through mergers in dense cities of stars? Or are they primordial seeds, sown in the fiery dawn of everything? The waves don't give a single answer yet. They reveal a universe more creative, more mysterious than our simple stories allowed. The soundtrack of collisions isn't just noise, it's the origin story of the dark universe, finally being told. Those silent collisions. They show us what's happening inside the most extreme objects we know. Neutron stars, when two of them spiral together, they're not perfectly rigid. They're soft in a cosmic sense. Their gravity pulls on each other, stretching them into teardrop shapes before they crash. That stretching, that tidal deformation, it leaves a tiny fingerprint on the gravitational wave signal, a whisper inside the chirp. And that whisper tells us how squishy the star is. That squishiness, it's everything. It tells us the nature of matter itself, crushed until a sugar cube would weigh as much as a mountain. On Earth, we can't reach these conditions. Our most powerful particle smashers, they only glimpse it for an instant. But a neutron star is a permanent laboratory of that extreme state. Its interior is a puzzle. We know it's mostly neutrons packed together, but under that pressure, do the neutrons break down into a soup of their parts, quarks and gluons? Does the core become something new? A strange form of matter like a superfluid or a solid crystal. Physicists call this the equation of state. It's the rulebook for how matter pushes back when you crush it beyond reason. And the gravitational waves, they're reading that rulebook for us. As the stars spiral closer, the tidal forces grow. A stiff star, one with a core that resists deforming, it holds its shape longer. It only distorts at the last moment. That puts a specific tweak in the waveform. A softer star, more deformable, it starts to stretch earlier. That changes the signal in a different way. By listening precisely, scientists can measure this tidal deformability. From the event in 2017, the data already told us something. Those neutron stars were relatively large and somewhat soft. That ruled out the most extremely stiff models. They're not impenetrable billiard balls. They have some give even at their core. Each new neutron star merger we detect, it sharpens the picture. It's like a blurry photograph coming slowly into focus. With enough events, we'll pinpoint the true equation of state. We'll know if there's a phase transition deep inside, where matter becomes something utterly alien. This is more than astrophysics, it's fundamental physics, using the cosmos as an experiment to probe the force that binds atomic nuclei under conditions we can't replicate. Those silent ripples from a catastrophic collision, they're answering one of the deepest questions. What is the ultimate fate of matter? The universe doesn't just speak in loud chirps. There's a murmur between the crashes, a faint, persistent hum. That's the gravitational wave background. It's the combined whisper of every black hole and neutron star binary that's ever spiraled together across the entire history of the cosmos. Millions of them, maybe billions, each one is too distant and faint to hear on its own, but together they create this stochastic hum, a cosmic static. A low-frequency vibration woven right into space-time. It's the sum total of the universe's violent history playing all at once, a choir of ghosts singing together. You can't pick out this sound with a single detector. It's a statistical signal, a subtle, correlated shift in the data, and that shift only emerges after listening for a very, very long time. Finding this hum requires a different kind of ear, one that listens for years, not seconds, and one that uses the cosmos itself as the instrument. That's where pulsar timing arrays come in. Astronomers use the universe's most precise natural clocks, millisecond pulsars. These are neutron stars spinning hundreds of times a second, beaming out radio pulses with metronomic regularity. They're lighthouses of incredible stability. The idea is elegant. As the gravitational wave background passes through our galaxy, it stretches and squeezes the space between us and these distant pulsars. That causes the arrival time of their pulses to shift by a tiny amount, a few tens of nanoseconds over a decade. No single pulsar shift proves anything. But if you monitor an array of dozens of pulsars across the sky, and you see the same pattern of correlated delays and advances ripple through them all, that's the signal. That's the fingerprint of the hum. It's like listening to an orchestra tuning up. You hear the collective noise before you can pick out the individual instruments. So what would this hum tell us? First, it would be a direct census of the universe's merger population, a holistic measure of how many binaries have merged over cosmic time. It could reveal populations of objects we haven't heard individually yet, like supermassive black hole binaries orbiting in the hearts of distant galaxies. Their mergers would rumble at these ultra-low frequencies, but the most profound possibility goes even deeper into the past. This hum could carry echoes from the universe's first moments. From the inflationary epoch, a fraction of a second after the Big Bang, when space itself expanded faster than light, the violent processes of that era could have generated primordial gravitational waves, stretched to these low frequencies by the expansion of the universe. Detecting that signal would be like hearing the birth cry of the cosmos. It would probe physics at energies 1 trillion times higher than anything our particle colliders can reach. A direct window into the grand unified theories that try to tie all forces together. So we listen, not just for the crashes that rewrite chapters, but for the hum that is the book itself. The ambient noise of creation waiting to be heard. That faint cosmic hum is the background noise, but to get the story, you need to see the actors. That's where the next revolution starts. It's a revolution of many senses. Gravitational waves were the first new messenger in a century, but the universe sends its news in many forms. There's light and ghostly particles, neutrinos, and high-energy cosmic rays. Each one is a different language telling a different part of the same story. And when you listen and look at the same time, the picture gets complete. That's multi-messenger astronomy. It turns every cosmic event from a single note into a full symphony. The neutron star merger in 2017 showed it perfectly. It was the first time we caught the same event with both ears and eyes. The gravitational wave detectors heard the final spiral and crash. 2 seconds later, gamma-ray satellites saw the flash. Then the whole astronomical world turned to look. Over days and weeks the aftermath glowed. In X-rays, ultraviolet, visible light, infrared, radio waves. A single event painted across the whole electromagnetic spectrum. Each type of light showed a different secret. The blue glow of the Kilonova told us about fast, light elements being thrown out. The red glow that came later revealed the slower, heavy elements, like gold and platinum forming. The radio waves that lasted for months showed the powerful jet of material that punched out from the wreckage. It's like investigating a car crash. The gravitational waves are the sound of the impact, the thud and crunch that tells you the speed and mass. The light is the skid marks, the broken glass, the bent metal. It shows the debris, the heat, the chemical traces left behind. And neutrinos, if we could catch them from an event like that, would be like seeing the airbags deploy inside the car. A direct signal from the heart of the explosive engine. Alone, each clue gives a partial story. Together, they reconstruct the whole incident. That coordinated effort turns astronomers into cosmic detectives with a full forensic toolkit. It lets us answer questions that were just speculation before. How does a jet of material moving almost at light speed form from the chaotic debris of a collision? The gravitational waves tell us about the central object left behind. The light across all wavelengths maps the jet's structure and energy as it plows into the space around it. This multi-dimensional view is rewriting the physics of the most violent explosions. It's not just confirming that gold is made in these crashes, it's understanding the precise recipe. The pressure, the temperature, the dynamics that forge it. Every new multi-messenger event adds another layer, turning the faint whispers of gravity and the fleeting flashes of light into a detailed, three-dimensional movie of cosmic creation. A single pair of ears has a limit. It can hear a sound, but it can't tell you where it came from. So for this to really be a telescope, it had to become a network. A web of listening posts around the world. LIGO had the first two in the United States. Then came others, Virgo, in the Italian countryside near Pisa. And KAGRA, built deep in a mine in Japan for quiet. Together they form this alliance, listening for tremors, and that network turns a sound into a location. It's triangulation, like how your brain locates a noise. When a gravitational wave passes Earth, it hits each detector at a slightly different time. The delay between it arriving in Louisiana, then Italy, then Japan, it's tiny. Thousandths of a second, but that delay is a map. By comparing the arrival times across the globe, scientists can trace the wave back to a patch of sky. Without the network, a detection from just LIGO might point to a huge area of sky, millions of stars. With 3 or more detectors, that area shrinks. From a continent down to a city, from a city down to a neighborhood, that precision is what made the neutron star discovery work. When that chirp came through, the data from LIGO and Virgo pinpointed its origin to about 30 square degrees. Still large but small enough, astronomers could point their optical telescopes there with a real chance, and they found it. That handoff from the ears to the eyes, that's the heart of multi-messenger astronomy. It turns a tremor into a full event we can study. The network adds confidence too. A signal in one detector could sometimes be a glitch. A signal seen in sequence by 3 detectors on different continents, that's real. It's the universe's signature, witnessed independently, and having detectors in different orientations lets them measure the polarization, how space is stretched and squeezed in different directions. It's a subtle test of Einstein's theory, how the waves behave as they travel through Earth's curvature. This collaboration is a model. Thousands of scientists from dozens of countries sharing data in real time, working toward a common goal. No one owns the sky's vibrations. The data is open, so astronomers everywhere can join the hunt or propose new theories. It's science without borders. Each new detector that comes online sharpens our hearing. It turns faint chirps into coordinates, and invites the whole world to look up and see what made the sound. Even this global network, though it's listening from the bottom of a deep, noisy well, the noise comes from Earth itself, seismic rumbles, ocean waves, the shifting of continental plates. It creates a low-frequency wall of sound, and ground-based detectors can't hear through it. It's like trying to listen to a symphony from outside the concert hall while standing in a thunderstorm. You might catch the high notes, the violins, the sharp crash of cymbals, but you'll miss the deep cellos, the thrum of the timpani, and the universe's grandest collisions, the most massive events. They play out in those deep bass notes. To hear them, you have to leave the storm behind. You have to go to space. That's the vision of LISA, the Laser Interferometer Space Antenna, a mission planned by the European Space Agency and NASA. It's not a single telescope, it's a constellation, 3 identical spacecraft flying in a vast triangular formation. They'll trail behind Earth in its orbit around the Sun, holding a stable formation where each craft is about 2.5 million kilometers from the others. A triangle with sides 5 times the distance from Earth to the Moon. Inside each spacecraft, a small, free-floating cube of gold and platinum hangs in near-perfect free fall, shielded from solar wind and cosmic rays. Lasers will constantly measure the distance between these cubes across the void. The principle is the same as LIGO, but the scale is cosmic. Instead of 4-kilometer arms on the ground, LISA has arms 2.5 million kilometers long in the pristine quiet of space. There's no seismic noise there, no rumbling trucks, just the pure silence of the vacuum, and that lets LISA tune its ear to an entirely new frequency band. The low hum, the long, slow waves that ground detectors are deaf to. What will it hear? The mergers of the true monsters, supermassive black holes. These beasts weigh millions or even billions of times the mass of our Sun, and they sit at the hearts of galaxies. When 2 galaxies collide over billions of years, their central black holes eventually spiral together, but their final dance is a slow, stately waltz. It can take months, even years, to complete a single orbit before the final merger. That generates gravitational waves with periods of hours or minutes, not fractions of a second. These are the waves LISA is built for. It will hear the crescendo as 2 galactic cores become one, an event that shakes the fabric of spacetime across the entire cosmos. But that's just the headline act. LISA will also hear the whispers of smaller objects falling into these giants, a process called extreme mass ratio inspirals. Imagine a stellar mass black hole or a dense neutron star caught in the grip of a supermassive black hole's gravity. It spirals in over thousands of orbits, tracing an intricate path through the warped spacetime around the monster. Each orbit emits a faint gravitational wave, a precise tracer of the extreme gravity field. By listening to that spiral, LISA will map the spacetime geometry around a black hole with unparalleled precision. It will test Einstein's theory in the strongest possible fields, searching for any deviation. It's like using a satellite to map the exact shape of a mountain by tracking a single pebble rolling down its slopes. And the potential goes even further back in time. LISA may be sensitive enough to detect the gravitational wave background from the very early universe with incredible clarity. It could hear signals from cosmic strings, hypothetical defects in spacetime from the first moments after the Big Bang, or catch the waves from the first generation of primordial black holes merging. It will be listening to the foundational bass line of cosmic history, a soundtrack that's been playing since the beginning, waiting for an audience quiet enough to hear it. This isn't just a new telescope, it's a new sense aimed at the slow, grand rhythms of a universe we've only ever seen in snapshots. That final hum from a black hole as it settles down, it's not just an echo. It's like a fingerprint, and there's this idea in physics, a really deep one, that says that fingerprint should be incredibly simple. It's called the no-hair theorem. A strange name, but it's a beautiful, almost philosophical concept. It says a black hole, for all its terrifying power, is fundamentally simple. It has no hair, no distinguishing features. When matter collapses into one, an unimaginable amount of information is lost. The star's composition, its magnetic field, its shape, its history, all of it is gone, swallowed beyond the event horizon. What's left can be described by just three numbers: its mass, its spin, and its electric charge. That's it. A black hole is the ultimate cosmic minimalist. From a chaotic, messy collapse, you get an object of stark mathematical purity. This is a direct prediction from Einstein's theory of general relativity. And now, gravitational waves give us the first real tool to test it out there in the dynamic universe. The test happens in that ring-down phase. After the violent merger, the new, single black hole isn't a perfect sphere. It's misshapen from the collision, vibrating like a struck bell, and according to the no-hair theorem, the way it vibrates, the specific frequencies it rings at, and how quickly those rings fade are determined solely by its final mass and spin. No other details matter. It should produce a clean, predictable set of tones, so scientists listen. They take the precise waveform from the ring-down and analyze its frequencies. They ask, does this pattern match what we expect for a black hole of this mass, this spin? So far, with the events we've detected, the answer has been yes. A resounding yes. The ringing matches the predictions of general relativity. The black holes we've heard appear to be bald, just as the theorem says. But we keep testing, because every confirmation also sharpens the search for a failure, for a deviation. If the ring-down frequencies were slightly off, if there were an extra, unexpected tone in that hum, it would be revolutionary. It would mean the black hole has a bit of hair after all. That hair could be a sign of new physics, maybe a hint of exotic fields predicted by theories beyond the standard model. Or maybe a subtle imprint of quantum effects at the event horizon, where our current understanding of gravity breaks down. Each new, louder merger we detect, especially of the most massive black holes, gives us a cleaner, stronger signal to scrutinize. We're using these cosmic collisions as the most powerful particle accelerators in existence, probing regimes of gravity and energy we could never recreate on Earth. The quest is to push general relativity to its absolute limit, to find the point where it finally cracks and a deeper theory must take over. We are listening for the whispers of quantum gravity in the fading ring of a newborn black hole. In the simplicity of its hum, we might find the key to the universe's greatest complexity. That final hum measures distance. Distance is everything in the universe. It's the foundation. For a century we've used the cosmic distance ladder. It's a chain. You start with parallax, the shift in a star's position as Earth moves. You use that to calibrate variable stars in nearby galaxies. Then you use those to calibrate supernova farther out. It works, but it's a ladder. Any small error on a lower rung, that error compounds as you climb. It distorts the whole view. Gravitational waves cut through that. They're a direct ruler, a standard siren. The principle is this: when we detect the waves from a merger, the loudness tells us how much spacetime was stretched here. But that stretch depends on two things: the intrinsic power of the source and its distance. A loud signal could mean a massive collision or a close one. That's where the waveform comes in. The shape of the Inspiral tells us the masses. Once you know the masses, you know the intrinsic power. It's like knowing the true wattage of a light bulb. From that, and from how faint the signal was when it reached us, you get the luminosity distance, the distance to the merger purely from gravity, no chains. No assumptions about other stars. Now for the cosmic part. Take a neutron star merger like in 2017. From the waves we got its distance, about 130 million light-years. But we also saw its host galaxy. From the galaxy's light, we measure its redshift, how much the universe's expansion has stretched that light. Redshift tells us how fast the universe is expanding at that distance. Combine the two, the direct distance from the waves and the redshift from the light. That gives you a single, clean data point for the Hubble constant. The expansion rate of the universe. This is key because right now, cosmology has a tension. Two methods disagree. Measurements from the early universe using the cosmic microwave background give one value. Measurements from the nearby universe using the distance ladder give a higher value. The difference is small, but it's there. It suggests something might be missing in our understanding or an error in the ladder. Standard Sirens offer an independent path. They bypass the ladder. Every neutron star merger with an optical counterpart is a new, unbiased point. Even black hole mergers, though dark, can contribute statistically if we associate them with a region of space. As we detect more, this new ruler builds its own map of expansion. We're not just measuring the universe by how it looks, we're measuring it by how it feels. By the tremors moving through it, each chirp is a story of a collision, but it's also a surveyor's mark, placed across the vastness, helping us triangulate the fate of spacetime itself. We get this squiggle from the detectors, a little tremor in the data line. To turn that into a story about colliding black holes, you need a library of possibilities. A cosmic dictionary. That dictionary is written with supercomputers solving the most complex physics equations. The challenge is Einstein's field equations. They describe how matter and energy warp spacetime and how that warping dictates motion. For a single, static black hole, the equations have a neat solution. But for two black holes spiraling together, the math becomes a nightmare. There's no clean pen and paper formula for their final merger. The only way forward is brute force computation. That's numerical relativity. Theorists take Einstein's equations and break them down into billions of points across a simulated volume of spacetime. They set the initial conditions, two black holes with specific masses, specific spins, on a specific orbital path. Then they let the simulation run. The supercomputer calculates step by tiny step how each point influences the others, how spacetime contorts and ripples as the black holes orbit faster and finally merge. The output is a predicted gravitational waveform, a precise template of what that specific collision should sound like, but one simulation isn't enough. The universe creates black holes with a vast range of properties, so scientists run millions of these simulations. They create a catalog of template waveforms covering every plausible combination of mass, spin, and orbital orientation. This library is the essential key. When a real signal arrives, the data analysis uses matched filtering. It's a cosmic game of find the match. Algorithms take the noisy detector data and compare it to every single template in that immense library. They search for the family of waveforms that most likely produce the faint chirp in the static. This isn't a simple visual comparison. It's a statistical marathon running on computing clusters, sifting through possibilities. Without these detailed simulations, the signals would just be noise. An indecipherable hum, the synergy is profound. The detectors provide the raw, whispered message. The supercomputer simulations provide the language to understand it. And every new detection tests and refines the simulations. If a signal has a feature the templates didn't predict, it sends the theorists back to their code to improve the physics. It's a continuous loop: prediction, observation, refinement. This collaboration between theoretical astrophysics, numerical relativity, and data science is the silent engine of the field. It turns a tremor in a vacuum tube into a story of two dark giants, spinning and crashing a billion light-years away. We're not just listening, we're learning how to understand the universe's deepest conversations. The Catalogue maps what we expect, but a new sense finds power in the unexpected. With every chirp we classify, astronomers are listening just as hard for a sound that doesn't belong. A signal with no template, a whisper that defies explanation. That's the frontier, the search for the exotic. In our own galaxy, there's a long-standing hope. To hear the birth cry of a black hole or a neutron star in real time, the gravitational collapse of a massive star's core during a supernova, it wouldn't be a clean chirp from a merger. It would be a burst, a messy, chaotic shout as the core implodes, rebounds, and rings like a bell. Detecting that would open a direct window into the most violent stellar death. It would show the asymmetries, the instabilities that shape the explosion, but these events are rare in our neighborhood. The signal would be complex and brief. It remains a holy grail, a potential signal waiting in the noise. Then there are relics from the universe's infancy, cosmic strings that are a prediction of some grand unified theories. Not strings of matter, but one-dimensional defects in spacetime itself, thinner than a proton but under immense tension. If they exist, they'd writhe and snap. They'd send out powerful bursts of gravitational waves. Detecting them would be a direct probe of physics at energies 1 trillion times higher than any collider. It would offer evidence for theories that try to unify all forces moments after the Big Bang. Similarly, theorists suggest the early, hot universe may have undergone dramatic phase transitions as it cooled. Like water freezing into ice, but for the fundamental fields of nature, those transitions could have sent vast ripples through spacetime, creating a stochastic background with a distinct signature. One we might detect. Our searches aren't just for cataclysms, they also listen for persistence. A solitary, spinning neutron star with a tiny mountain on its crust, a minuscule asymmetry, wouldn't be a perfect sphere. Its rotation would produce a continuous, monochromatic hum, like a cosmic tuning fork. Finding that continuous wave would let us peer inside these dense objects in a new way. We could measure the strength of their crystalline crusts, and all the while the hunt continues for that primordial stochastic hum, the combined whisper from inflation and from countless unresolved sources across all of time. This open-ended listening is what makes the field thrilling. We built these ears to hear black holes, and they have, but they're now tuned to the cosmos at large. With no guarantee of what comes next, the most transformative discovery may not be a louder version of what we know. It could be a tone, a pattern, a rhythm no theorist ever predicted. A signal that forces us to rewrite the textbooks from the first chapter, that embodies the purest spirit of exploration, to open a new window on reality. And to have the humility to wait for the universe to show us what we didn't even know to look for. This new window isn't private, it's open, the data is shared. The whole science is built on radical transparency, on global collaboration. When they confirm a detection, they release the data to the world, not just the polished results, the raw squiggles. The same signals the scientists use. So a student in a classroom, an amateur with a telescope, a researcher at a university without $1 billion observatory, they can download that data. They can run their own analysis, test their own ideas, make their own discoveries. It democratizes the frontier, turns the most esoteric physics into a playground. For curious minds everywhere, that open approach accelerates discovery. More eyes, more minds working on the same puzzles from different angles, but the collaboration goes deeper. It invites the public not just to see, but to do the work. Projects like Gravity Spy, the detectors, for all their precision, aren't silent, they're filled with glitches. The constant hum of the Earth, a truck passing miles away, a tiny fluctuation in the laser, the shifting of the mirrors, they all create noise, patterns in the data that can look, for a moment, almost like a real signal. Distinguishing a true cosmic chirp from thousands of these instrumental murmurs, that's a monumental task. Computers are good, but the human eye and brain are still exceptional. At pattern recognition, Gravity Spy shows volunteers snippets of detector data. It asks a simple question: what does this look like? A clean, arching chirp. Or a scattered blob, a sharp line, a repeating whistle. By classifying these glitches, people around the world are training the machine learning algorithms. They're teaching the computers what to ignore. Every click from a volunteer makes the detector's hearing a little more acute. It turns the global public into part of the research team. Citizen science at its most profound. You don't need a PhD to contribute to Nobel Prize-winning physics. You just need curiosity, a willingness to look. This model does more than improve data. It demystifies the process of big science, pulls back the curtain on the messy, human work behind the elegant headlines. Shows that discovery isn't a single eureka, a moment in a lab. It's a collective, often tedious, sifting of possibilities, and in doing that, it builds a global community. People from all walks of life connected by the shared wonder of listening to the universe. They're not passive spectators, they're active participants. In the greatest detective story ever told, helping to tune the ear of humanity, to hear the whispers we've waited a century to understand, it transforms cutting-edge astrophysics. From a distant, elite endeavor into a deeply collaborative human project, the quest to understand the cosmos, it belongs to everyone. The tools we built to listen for gravitational waves. They're these incredible feats of engineering, 4-kilometer arms, a perfect vacuum inside, lasers bouncing between mirrors that hang completely isolated. It's all about precision, but that precision, the technology that came out of it, it didn't just stay in astronomy. It started to find uses here on Earth. Because to measure something that small, a tremor smaller than a proton, you have to push everything, and that push created new tools. Take the lasers. The ones at the heart of LIGO, they had to be unbelievably stable, a pure single frequency. The light waves, they're like a perfect series of waves. Unbroken for kilometers, that kind of laser, that stability, it's become a key tool for something else, quantum computing. In quantum systems, you often use laser light to control particles. Atoms, ions, the stability they developed for LIGO, that gives the control you need for delicate operations to build more reliable quantum processors. Then there's the silence. To hear the universe, you have to quiet the Earth, the seismic isolation. It's a system of pendulums, filters, actuators. It creates these pockets of stillness. And that technology, it went straight into manufacturing, high-precision manufacturing, in semiconductor plants where they etch circuits at the nanometer scale. Any vibration, the tiniest tremor, it can ruin a silicon wafer. The damping techniques from the observatories, they help create the stable environment you need. To build the next generation of chips, it helps medical imaging too. Advanced microscopes, they get sharper images when they're isolated from vibration. And the data, the detectors produce a torrent of it, just a continuous stream of noise. Finding a faint chirp in all that, it's a huge signal processing challenge. The algorithms they built, the machine learning models to sift through it, they've gotten incredibly sophisticated, and now they're being used for other things. To analyze seismic data, to understand earthquakes better, or to process medical scans, to find the early, subtle signs of disease. The same skill that finds a black hole merger in noise can find a hidden fault line. Or a faint tumor, even the vacuum. The beam tubes are at a vacuum 1/1,000,000th of Earth's atmospheric pressure to eliminate noise from air molecules. Maintaining that over such a huge volume, it required new techniques in sealing, in pumping. Those advances apply directly to industrial processes where you need an ultra-clean environment. Coating advanced optical lenses, fabricating sensitive satellite components. So this whole effort, it started with a question: what does the universe sound like? A curiosity-driven question, but to answer it, you have to solve a chain of practical problems, seemingly impossible ones, and in solving them, you create these tools. This knowledge, and it ripples outward. It transforms other fields. It helps build better computers. It helps us see more clearly into the human body. It helps manufacture tomorrow's technology. The ear we built for the stars, it ended up giving us a finer touch for the world right here. A detection's triumph is built on near constant noise. Every chirp is a signal pulled from a sea of interference, a whisper isolated from a roar. Running a gravitational wave observatory isn't passive listening. It's a war, a sophisticated, relentless fight against the universe's background hum and our own planet's restless activity. The goal is to create a bubble of near-perfect stillness on a world that never stops moving. The largest enemy is the ground. Seismic noise is a constant rumble. It comes from earthquakes thousands of miles away, from ocean waves crashing on distant shores, their energy moving through the planet's crust. Even from human activity, logging operations, train lines, highway traffic, all of it sends tiny vibrations through the Earth, threatening to shake the delicate mirrors. To combat this, the mirrors don't just hang, they're suspended in a 4-stage pendulum system. Each stage filters out vibrations of a specific frequency. It's a multi-layered shock absorber for spacetime itself, isolating the mirrors from the jittering world below. Then there's noise from warmth. At room temperature, the atoms in the mirror coatings and their suspensions are in constant motion. They jitter. This thermal noise creates a faint, fundamental limit to how still the mirrors can be. One solution is to go cold. Future upgrades, next-generation detectors, they plan to use cryogenics. Cooling components to temperatures near absolute zero. That dramatically reduces the thermal jitter. It freezes the atoms into a quieter state. Perhaps the most fascinating challenge comes from the quantum world. The very laser light used to make the measurement introduces noise. Because of the Heisenberg uncertainty principle, there's a fundamental fuzziness to the vacuum of space. Even in complete darkness, virtual particles flicker in and out of existence. This quantum noise shows up as photons randomly appearing and pushing on the mirrors, and as a fundamental uncertainty in the phase of the laser light itself. You can't measure the position of a mirror with infinite precision without disturbing its momentum. It's a bedrock law of physics, so scientists have begun to fight quantum with quantum, using a technique called quantum squeezing. They manipulate the uncertainty. They trade precision in one property, like the photon's phase, for greater precision in another, like its amplitude. It's a way to reshape the fundamental quantum noise, to make it quieter in the specific frequency band where they're listening. They are engineering the vacuum itself to hear more clearly. This battle defines the work. Teams of engineers and physicists monitor hundreds of environmental channels in real time. Microphones, seismometers, magnetometers, weather stations. They track every potential disturbance. When a glitch appears in the data, the first question isn't, is this a black hole? It's what on Earth or in the instrument caused this? Meticulous calibration runs happen daily. They fire precise forces at the mirrors to map the detector's response. Understanding the noise isn't separate from detecting a signal. It's the prerequisite. Every confident chirp in the Catalogue isn't just a discovery from deep space. It's a victory in an ongoing campaign, a testament to carving out a bubble of exquisite silence on a noisy planet. To hear the faintest tremors from the edge of reality, every chirp means a collision, but for a collision you need a pair, two objects bound together, close enough to eventually spiral in. That leads to a puzzle. How do these pairs form? How do they get so close? It's about stellar lives and deaths and the places they live. Astronomers see two main paths. Two different kinds of neighborhoods. The first is a partnership from birth, isolated binary evolution, two massive stars born together from the same gas cloud. They orbit from the beginning. They live their lives, one often feeding the other. The more massive one runs out of fuel first. Its core collapses, a supernova. If the explosion isn't too violent, it leaves a neutron star or a black hole. The system survives, but the supernova gives the remnant a kick, a recoil that changes the orbit. Then the process repeats when the second star dies. Through all this, the two remnants stay bound. Over eons, they spiral closer from gravitational waves until they merge. That's a quiet, isolated life playing out in the sparse disk of a galaxy. The second path is more social, more chaotic, dynamical formation. This happens in dense stellar cities. The cores of globular clusters, spherical swarms of hundreds of thousands of stars packed incredibly tight. In a crowd like that, the heaviest objects sink to the center. Black holes, neutron stars, they sink through gravitational interactions. They engage in a complex dance, swapping partners, ejecting lighter stars, occasionally finding a lasting companion. When two of these dark remnants form a close binary through these encounters, they can merge. That's finding a partner later in life, in a very busy place. The gravitational wave signals give clues. The spin of a black hole is like a fingerprint. In the isolated binary where the stars evolve together, their spins are often aligned with the orbit. They've been dancing together their whole existence, but in a dynamical encounter, two black holes find each other randomly. Their spins are likely misaligned, tumbling in all directions relative to their orbit. By measuring the spin orientations, astronomers can deduce the origin. The data so far shows a mix. Some pairs have aligned spins, a quiet, shared life. Others have random spins, a dramatic meeting in a stellar metropolis. The masses tell another part. Hierarchical mergers in dense clusters can build exceptionally heavy black holes, ones difficult to form from a single star. So when we detect a merger with a total mass far beyond typical expectations, it points toward the dynamical path. Each new detection adds a data point. We're not just cataloging collisions, we're mapping the social lives of stellar corpses across different galactic environments, learning which neighborhoods are quiet retirement communities and which are chaotic downtown hubs, where dark remnants constantly meet, pair up, and crash. The silent tremors from these mergers are rewriting stellar destiny, from quiet birth in a nebula to a final, violent embrace dictated by the crowd. The hum fades, but the story keeps going. The new object isn't just sitting there, it's an actor, and its first act can be leaving. When two black holes merge, that last burst of gravitational waves isn't always symmetrical. If the original holes had different masses, or if their spins were off, the final pulse can shoot out stronger in one direction, like a rocket engine. That lopsided blast has recoil. It can kick the new black hole, a gravitational rocket. The kick can be huge, hundreds, even thousands of kilometers per second. If the merger happened in a loose star cluster, that kick is an ejection. The black hole gets thrown out into the dark between galaxies, a high-speed wanderer stripped of its neighborhood. A rogue drifting through the emptiness, a dark ghost from a violent past. Even inside a galaxy's core, a strong kick can displace it, send it on a long, oscillating orbit through the galactic center, heating the stars around it. The collision's echo doesn't just ring, it can throw the product of the violence out into the cosmic dark. For neutron stars, the aftermath is a race. The merger creates something hot and hypermassive. For a few milliseconds, it's the densest thing around. Its fate is on a knife's edge set by a critical mass. If the combined mass is below that line, the remnant might hold. Supported by frantic spin and extreme pressure, it becomes a heavier neutron star, a rapidly spinning magnetar with a magnetic field a quadrillion times Earth. But if the scale tips even slightly over that limit, nothing can hold it up. In a fraction of a second, it succumbs. The whole object, a city's worth of ultra-dense material, collapses inward. A new black hole is born, not from a star's death but from collision wreckage. But before that collapse or around it, the event scatters a fortune. The violent collision flings out shrapnel, not metal chunks but a dense, neutron-rich fog of atomic nuclei. In that expanding cloud, conditions are perfect for rapid neutron capture. Atoms gorge on free neutrons, climbing the periodic table in heartbeats, forging gold, platinum, uranium. This enriched material, this celestial fallout, gets blasted into the surrounding space. It mixes with the primordial hydrogen and helium, becomes part of the raw material for the next generation. When new stars and planets form from that enriched cloud, they'll already carry the seeds of these heavy elements. The gold in a future mountain, the platinum in a future asteroid, the iodine in a future ocean, all might carry the signature of that ancient crash. A single merger can pollute an entire dwarf galaxy with precious metals, changing its chemical destiny forever. So these collisions aren't just spectacular endings, they're engines of transformation. They redistribute mass and energy on galactic scales, sending dark remnants speeding through the void. They are the primary forges for the universe's heaviest elements, directly seeding the cosmos with the building blocks for rocky planets and, maybe, for life. The gravitational wave is just the announcement. The real work, the chemical enrichment, the dynamical stirring echoes for billions of years, quietly shaping how galaxies evolve. Each chirp we hear is the start of a new chapter in a very long story. Each chirp isn't just a point in space, it's a moment in time. The redshift of the source tells us exactly when in the universe's history that collision happened. A signal from 1 billion light-years away shows us an event from 1 billion years in the past. And when we collect these signals from different distances, we're not just taking a snapshot. We're doing cosmic archaeology. We're digging through layers of time to see how the universe's violent habits have changed. That lets us trace a historical narrative. We can ask, did mergers happen more often in the young, crowded universe? Or did they peak at a certain cosmic epoch? The answer is in the timing. Massive stars live fast and die young. They collapse into black holes and neutron stars in tens of millions of years. But for two of these remnants to then spiral together and merge, that takes much, much longer. Billions of years of slow gravitational decay. So a peak in the merger rate we see today should correspond to a furious burst of star formation that happened long, long ago. By mapping the merger rate across cosmic time, we're indirectly charting the epic story of star birth throughout the cosmos. We're watching the delayed echo of the universe's most fertile periods. But the story gets richer. The properties of the merging objects themselves might have evolved. In the early universe, stars were made of almost pure hydrogen and helium. They lacked the heavy elements that act as a coolant during star formation. That lack may have led to the birth of truly monstrous stars, hundreds of times the mass of our Sun. The black holes they left behind could have been different, potentially more massive or with different spin characteristics. By detecting mergers from very high redshifts from the universe's first few billion years, we might catch the signatures of this primordial stellar population. We could be listening to the collisions of the universe's first generation of dark remnants, and then the environments where binaries form and survive may have changed over time. In the dense, chaotic conditions of the early universe, dynamical encounters in star clusters might have been the main path to mergers. Later, as galaxies settled and thinned out, isolated binary evolution from peaceful stellar nurseries might have taken over. The mix of aligned and misaligned spins we measure, when sorted by the age of the universe, could reveal this shifting balance. It tells us not just how many mergers happened, but how they happened as the cosmic landscape matured. This temporal dimension turns a catalogue of events into a living history. We're not just counting collisions in the dark, we're watching the merger history of the universe unfold in slow motion. From the frantic, crowded conditions after the first stars ignited to the more measured pace of the modern cosmos, each new detection adds a data point to this grand timeline. It helps us understand how the populations of compact objects have grown and evolved and shaped the galaxies around them across nearly the entire age of existence. The deepest echoes might not come from collisions. They could be something else, a faint, primordial hum from the very beginning of everything. This is where gravitational wave astronomy connects to the most fundamental physics questions. It goes beyond mapping black holes. It becomes a direct probe of the universe's first moments. The energy scales here are almost unimaginable, far beyond what the Large Hadron Collider can reach. Beyond any machine we could ever build, to test the physics of that time, we need a natural experiment, one of cosmic proportions, and the results of that experiment might be written in gravitational waves. Take the theory of cosmic inflation, the idea that a fraction of a second after the Big Bang, the universe went through a period of exponential expansion. Faster than light expansion, this theory explains a lot: the overall flatness of the cosmos, its uniformity, but it also makes a specific prediction. That violent inflationary process should have generated a background of primordial gravitational waves. Those waves would have been stretched over the last 13.8 billion years. By the expansion of the universe, today they would be a faint, persistent signal in the lowest possible frequency bands, a whisper from the dawn of time. Detecting that signature would be a direct window into physics at energies a trillion times higher than we can create. It would be evidence for inflation itself. And it would tell us about the specific physics that drove it. Then there are the grand unified theories, attempts to describe how the four fundamental forces were once a single, unified force. In the extreme heat of the early universe, gravity, electromagnetism, the strong and weak nuclear forces, as the cosmos cooled, it underwent phase transitions. Like water freezing into ice but for the fabric of reality itself, some theories say these transitions were violent, first-order events. Bubbles of the new phase of the universe would have formed and collided. That turbulence would have sent powerful ripples through spacetime, ripples that would persist today as a characteristic hum in the gravitational wave background. Finding that specific pattern would be like discovering a fossilized imprint of the moment the forces of nature split apart. It would point us toward the correct theory of everything. Even the waves we already detect carry subtle clues. Einstein's theory assumes the graviton is massless, like the photon. That's why gravitational waves travel at the speed of light. But what if the graviton had a tiny mass, almost imperceptible? This would cause the waves to disperse very slightly over cosmic distances. Higher frequency waves would arrive a minuscule amount later than lower frequency ones. By comparing arrival times from a single, loud merger event, we could place incredibly tight constraints on the graviton's mass. So far, every observation confirms it is vanishingly small. If it has any mass at all, but each new, more distant event sharpens this test. And what about the radical ideas from string theory? Some versions suggest our universe has more than 3 spatial dimensions. There could be large extra dimensions, curled up or existing parallel to our own. The presence of these dimensions would alter how gravity behaves, especially in the strong field regime of a black hole merger. It could affect the ringdown of a newly formed black hole, or change how gravitational waves propagate. While no evidence for extra dimensions exists yet, the precision of gravitational wave observations provides a new laboratory. A cosmic-scale laboratory to search for their signatures. In this way, every chirp is more than an astrophysical event. It's a test of the deepest laws. The collisions of black holes and neutron stars are natural particle accelerators of unimaginable power. They create conditions we cannot replicate. Probing gravity in its most extreme form, and the silent hum between them may carry the encoded history of creation itself. We are no longer just astronomers. We are archaeologists of spacetime, sifting through its vibrations for the fingerprints of the first moments, listening not only to what the universe is, but to how it began. This detective story is also a classroom, the whole journey to hear the cosmos, starting with a single equation and ending with this global network of ears. It's more than just a scientific triumph. It's a masterclass in how curiosity actually works. You see a century of patient collective effort. Einstein had a hypothesis, one he doubted himself. Then came decades of technological dead ends and quiet perseverance. And then the international collaboration, the open sharing of data, and that moment of discovery that rewrote all the rules. That narrative is a perfect vehicle for education. It makes the scientific method tangible, not as some dry list of steps in a textbook, but as a living, breathing human adventure. Full of setbacks and breakthroughs, outreach programs from the observatories bring this story directly to students. They don't just talk about black holes. They let young minds play with the data. The same chirps that won a Nobel Prize, they're available online for anyone to analyze. Interactive exhibits let visitors try to isolate a signal from simulated noise. So they feel the challenge and the thrill firsthand. Documentaries show the faces behind the science, the engineers, the programmers, the theorists. That makes the pursuit relatable. It demystifies the process. It shows that science isn't done by distant geniuses in ivory towers. It's done by teams of diverse, dedicated people solving practical problems. That a career in science can mean working on a laser system one day and analyzing a signal from a billion light years away the next. And most importantly, it connects the abstract to the concrete. The idea of curved spacetime can feel impossibly remote, but when you hear a chirp and you understand it's the sound of that curvature ringing from a collision, the concept clicks. It has weight, it has a sound. Students see that the most fundamental questions, what is space, what is time, how did the universe begin, they're not just philosophical musings. They are questions you can build machines to answer, you can point to evidence, you can hear the proof. That inspiration is perhaps the field's most enduring legacy. Beyond the catalogue of collisions and the tests of relativity, it's cultivating the next generation, scientists, engineers, curious minds. It demonstrates that the universe is not a static backdrop. It's a dynamic, violent, and astonishing place, still full of mysteries waiting to be solved, and it invites everyone to listen in, to learn the language of its vibrations, and to imagine what they might one day hear. This new astronomy, its success, it forces a kind of humbling truth on us. For all of human history, the cosmos was what we could see. Our map of reality was built by sight, but gravitational waves show that map was missing continents, entire continents, a major part of the universe, the dark, massive remnants of dead stars, their collisions. It was hidden. Completely hidden, a silent narrative running parallel to the story light tells, that challenges any idea that the universe is arranged for us for our observation. It wasn't, we just built the right tool and a new chapter opened. It makes a philosophical point. To understand the cosmos, we can't rely on our natural senses alone. We have to extend them, build new senses through technology, through imagination. The ear we built for spacetime, it's a prosthetic, a technological sense organ. It gives us access to a layer of existence light can never show, and it makes you wonder, what else are we missing? What other cosmic phenomena are we blind to, deaf to, simply because we haven't conceived of the instrument yet? The universe probably holds more surprises, phenomena that don't interact with light or gravity in ways we currently understand. That's not a failure of science. It's the promise. The horizon of the unknown keeps receding. It invites us to build the next sense, to listen for the next whisper. On an ethical level, This was a monumental investment in pure curiosity. Billions of dollars, decades of work, faith in a century-old mathematical prediction, pursued with no guarantee of success. That investment has paid dividends. Not just in knowledge, in tangible technology, in global cooperation, in inspiring generations. It argues for the value of understanding for its own sake. Of seeking to know our place, not for profit, but to fulfill a human drive, to explore, to comprehend. We listen to a dynamic cosmos now, often violent. We hear the crashes that forge the elements of life, that scatter dark remnants across the void. This knowledge doesn't diminish us, it situates us. We are witnesses to a grand, ongoing story. Construction and destruction on scales and timelines far beyond us. Yet through ingenuity, through collaboration, we found a way to tune in. The universe isn't a silent painting. It's a symphony of spacetime, often brutal but ultimately knowable, and we have, at long last, learned how to hear the music. The horizon isn't a limit. It's a promise, and the ears we have on the cosmos right now, they're being tuned for a much more sensitive future. LIGO, Virgo, KAGRA, these aren't static monuments. They're living instruments, they're always being upgraded, their lasers are refined, their mirrors are made quieter, quantum squeezing techniques are perfected. The goal is to push sensitivity to new extremes. In the coming years, these enhanced detectors could hear cosmic collisions not as rare events, but as a regular rhythm. We could go from a few detections per month to a daily cadence, maybe even hourly. The universe's violent soundtrack, once a distant whisper, could become a constant background hum in our data. That deluge of signals would change the field, from discovery to detailed demography. We wouldn't just know black holes merge, we'd have a vast statistical catalogue, mapping their populations across cosmic time with incredible precision. But the ambition goes beyond upgrading what we have. On the drawing boards are the third-generation detectors. Projects like the Einstein telescope in Europe and Cosmic Explorer in the United States, these aren't mere improvements, they're leaps into a new realm of hearing. Their designs are breathtaking. The Einstein telescope envisions a triangular underground facility with 10-kilometer arms, a shape that improves its ability to pinpoint sources. Cosmic Explorer proposes one 40-kilometer arm, or even two 40-kilometer arms in an L shape, an order of magnitude larger than LIGO. The sensitivity gain isn't linear. It's transformative. These observatories could be 10 times more sensitive than our current best. What does that mean? It means hearing so far out into the universe that they could detect every single merger of two stellar mass black holes. Anywhere in the cosmos, the entire population would become audible. No event would be too faint or too distant. We'd have a complete census of stellar death spirals across the observable universe. And while these colossal ground-based ears listen for the high-frequency chirps, a symphony in space will tune into the bass notes, the laser interferometer space antenna. LISA, that's the next frontier. By placing its 3 spacecraft millions of kilometers apart in the quiet of space, it will hear frequencies too low for any ground instrument. Its domain is the slow, grand dance of the supermassive. It will listen for the mergers of black holes that anchor entire galaxies, events that shake spacetime for months or years. It will hear the faint spirals of smaller objects into these giants, mapping the warped geometry around them with exquisite detail. LISA will open a window on a slower, more majestic scale of cosmic violence. One that's been completely silent until now. Meanwhile, another patient effort nears a historic threshold. Pulsar timing arrays, that network of cosmic lighthouses. They're collecting more data with every passing year. The subtle, correlated shifts in the arrival times of their pulses are building toward a statistical certainty. They're on the verge of a monumental announcement, the definitive detection of the gravitational wave background, that faint hum from all the merging supermassive black holes throughout cosmic history. It would be the first direct evidence of this predicted chorus, a background noise that's been permeating the universe since the first galaxies began to collide. This multi-band future is the true goal, to listen to the universe across the entire gravitational wave spectrum, from the highest chirp to the lowest rumble. It will be like having hearing that ranges from the buzz of a bee to the deep resonance of a pipe organ. With this full spectrum hearing, we'll be able to trace the life cycle of black holes. From their first collisions in the early universe to their final mergers in galactic cores billions of years later, we'll connect the dots across time and scale, building a unified narrative of how dark structures shape the cosmos. The story of cosmic collisions, once written in invisible ink, is about to be printed in bold. Across every page of our understanding, the true destination is that unified story. It started with an equation, just a mathematical whisper about ripples in the fabric of reality. For 100 years, it was a beautiful idea stuck in theory. Then came the long work of engineering, building an ear delicate enough to hear the faintest tremors in the universe. That first detection in 2015, that was the moment the whisper became a shout. A prediction turned into a whole new science, but that was just the beginning. What came after has been this symphony of connections. Gravitational wave astronomy isn't a curiosity anymore. It's the thread. It's weaving together different chapters of how we understand the cosmos. It connects the death of a star to the beginning of planetary chemistry. We used to think heavy elements like gold were made in supernova, but the waves and the light together showed us the real place. The collision of two neutron stars, that event didn't just confirm a theory, it put us and our world right inside that story. The atoms in our bodies, the metals in our tools, they carry that legacy. From ancient, violent collisions in the dark, the death of stars is linked to the ingredients for life, and it ties the growth of the largest structures to the expansion of the universe itself. By giving us a direct ruler, a standard siren, these waves offer a new way to measure how the universe is accelerating. They skip the whole cosmic distance ladder. They give us an independent check on one of cosmology's biggest puzzles, the collisions of black holes. These events of incredible localized violence become tools for measuring the grandest, smoothest motion there is, the stretching of space, and most of all, it bridges the physics of the huge and the tiny. The mergers we hear test Einstein's gravity in the most extreme places. But in doing that, they probe questions for quantum mechanics, the nature of matter at nuclear density inside a neutron star, the possible existence of extra dimensions, the properties of the graviton. We're using collisions of objects millions of kilometers across to investigate rules for particles smaller than an atom. The cosmos becomes our lab. Its most violent events are our experiments. This is the birth of a new sense. For all of human history, we saw the universe through light. Now we perceive it through the vibrations of spacetime. This isn't just a better version of our old map. It's the discovery of a new continent on that map. A dark, dynamic continent where collisions shape galaxies, forge elements, test the laws of physics. The story isn't inferred from silent pictures anymore. It's heard directly in the rising chirps and the fading hums that echo from deep in time and space. We're not just watchers of the cosmic fire now. We're listeners to its rhythm, and the story it tells is richer, more violent, and more beautifully connected than we ever imagined. That first signal back in 2015. It was just a single note. Now we're hearing a whole symphony, a chorus of collisions, and it's rewriting the cosmic story as we listen. Gravitational wave astronomy didn't just add another tool. It changed our relationship with the universe. For thousands of years, we were spectators, watching a silent movie of light against the dark. Now we're listeners. We've tuned our ears to the vibrations of spacetime itself. We hear black holes in their final dance. We hear neutron stars crashing together. That's the forge for cosmic gold. And in the quiet hums between the crashes, we might even hear the remnant rumble from the universe's first moments. This new sense has solved mysteries we didn't know how to ask. It answered where heavy elements come from, not with theory but with the direct evidence of a glowing kilonova. It revealed a hidden population of massive black holes. A dark society we never knew was there, and that poses new questions. How do these dark giants form? Could some be primordial fossils? What does a black hole's ringdown tell us about quantum gravity? Every answer leads to a deeper mystery. This whole journey is a monument to human curiosity and to breathtaking technological ingenuity. It's the story of taking a century-old mathematical prediction and, through decades of work, building an ear delicate enough to prove it true. That process itself, the global collaboration, the open data, the war against noise, that's as much a part of the discovery as the chirps from the void. Looking ahead, the horizon is full of promise. Space-based observatories like LISA will tune into the low-frequency hum of supermassive black holes. Third-generation detectors on Earth will hear every stellar collision in the observable universe. Pulsar timing arrays are on the verge of revealing the gravitational wave background, the combined whisper of all cosmic history. Each new detection, each more sensitive instrument, adds another layer to the story. It refines our map of this dark, dynamic continent we've only just discovered. This isn't a finished book. It's a living narrative. Every new ripple in spacetime rewrites a paragraph, or challenges an assumption, or opens a whole new chapter. We're not just reading the universe anymore. We're listening to it tell its own story, in its own voice. And it's a story of breathtaking violence and profound creation and endless wonder.